Hello, welcome back. In our previous class, we have talked a little theories on probabilities, and we have talked how same x's do not lead to same y's. In this class, I want to go briefly into calculations involving Bayes' theorem. Bayes' theorem is actually made out of conditional probabilities and multiplicative rule. So let's check on the development basis of Bayes' law. Allow me to insert a new slide here. All right. So let's say we already know that from multiplicative rule, probability of A intersection B is equal to probability of A given B times probability of B. Right? We have already seen this. The next probability, of course, now when you interchange this, there will be no changes, right? You know that. Of course, B intersection A is the same as A intersection B, but this right hand side can be different. Probability of B given A, all right, times probability of A. So this other side can be written in this other way, but the left side is remaining the same. But again, we know that probability of A given B is equal to probability of A intersection B, right, divided by probability of B. All right? Yes. So these are the bases that we have to have. We have this from conditional probability, and we have this from multiplicative rule. Now you can replace probability of A intersection B with this, so which will be equal to probability of B given A, right, times probability of A divided by the probability of B. All right. So probability of A given B is equal to probability of B given A times probability of A divided by probability of B, and we say this is Bayes' theorem. Bayes' theorem. Bayes' law. All right. So probability of A given B is probability of B given A times probability of A divided by the probability of B. But if you have many B's here, right, you can extend this formula to something like this. If you have many of maybe the first coming ones are many, BI, probability of BI given A is equal to probability of A given BI times probability of BI, just something we had up there, and then divide by probability of A given BI B1, for instance, times probability of B1 plus, here we have B1 plus probability of A given B2 times probability of B2. Of course, this one you have seen in the law of total probabilities and so on. All right, so this is also Bayes' law. So this one we can take it as Bayes' law. Bayes' law, right? Okay, now I want us to take an example, just the one I've mentioned before. Let's say you have gone to a hospital and you are tested positive. I don't know if I should say fortunately, I don't know, or unfortunately. Okay, it doesn't matter. You have went to hospital and you have tested positive. So how much should you be worried? So probability of HIV, you having HIV given the test is positive, should be equal to, from here, probability of from our example up here, right? Probability of positive given HIV times probability of HIV and divide by probability of positive. All right, we said that here. Probability of A given B is equal to probability of B given A times the probability of A divided by the probability of B, which is probability of this is multiplication, probability of positive. All right, let's try to break down what each of this means. Let's start with our numerator. All right, so our numerator, probability of positive given HIV is all right, let's first have all of this times probability of HIV. So probability of positive given HIV is what we call sensitivity of test. So this is sensitivity of test. Sensitivity of test. So what is the probability that if you have HIV, the test you get is positive, right? So those people who have created the kit, the manufacturer will give you this. Manufacturer will give the sensitivity of the test. All right. Then probability of positive is an incidence rate, or just incidence, not incidence rate, incidence. So what portion of population is HIV positive? So probability that anyone who is selected at random from a certain city or from a certain country or a certain country is being positive. So that is what we have as probability of not positive, sorry, as the probability of HIV. HIV. So get this, not the probability of positive. So these are what we are going to have. So let's say, let me insert another slide. Let's say sensitivity test of the kit according to manufacturer is 0 point sensitivity I wish even I should have taken an example of COVID-19 test, not even this one anyway. So sensitivity test according to the manufacturer is 90, let's say is 99%. So probability of positive given HIV is equal to 0.99 according to manufacturer. Great. So probability and let's say the incidence rate, okay, incidence of this population is, let's say, 1%. So probability of HIV for anyone in this population is at 0.01, right? Or this is the probability. All right, we have our numerator. Our num is there. So our denominator, let's come to our denominator. It is probability of positive. So we have two probabilities of positive. There is two possibility. That is probability of positive given HIV, all right? And we have probability of positive given not HIV. So there are two ways that you can be told you are positive. One, you have HIV, you are positive given HIV, or you are positive but not having the HIV. All right. So how can we go around this? Probability of let's have our formula, right? Let's first now type our formula. Probability. Now these are here we can use how many ways you can be positive. So we can use laws of total probability, right? Here we are going to use law of total probability, where positive is contributed by when you are HIV positive, or you can even told be positive when you are not really HIV positive. So probability of HIV given positive is equal to probability of positive given HIV, which we said is sensitivity test, times probability of HIV, which we said is incidence that you get from epidemiology report. Now here at bottom we are going to have probability of positive given HIV, positive given HIV, times probability of HIV from law of total probability, plus probability of positive but not HIV you can be told you are positive but you are not having HIV, times probability of not HIV. Now we almost have everything for our calculation. So we say probability of positive given HIV is a sensitivity test, which is 0.99 times probability of HIV is incidence rate, which is 0.01, right? Divide by probability of positive given HIV. Probability of positive given HIV, we have said, is 0.99 times probability of HIV, we said, is incidence rate, which is 0.01 plus, now probability of HIV given not positive. So this one is the error part. So it will be, since this one is 0.99, here we are going to have 0.01, because we say 1 minus 0.99 times probability of not positive. So probability of not positive is again subtracted from an incidence rate, so it will be 100 minus 1%, which is 99%. So here we are going to have 0.99. Alright, probability of not positive is this. It is 1 minus incidence, and probability of positive but not HIV is 1 minus incidence. So we have everything we have here. So let's say how much you should be worried. So is equal to 0. Let me open my calculator here. Right, let me open my calculator here. .99 times 0.1. We are going to 0.01. So we are going to have it here as 0.0099. That is our numerator. Divide by 0. Okay, we have the same 0.0099 plus, what are we adding it to? 0.001 times this, so there is still the same 0.0099. So what do we get here? Plus 0.0099. Alright, so we are getting as 0.0099 divided by 0.0198. Right, what do we get if we divide this? 0.0099 divided by 0.0198. right? So we get 0.5. Really? Alright, let me see if we have everything line. Probability of HIV 0.01. Alright, 0.99, 0. This, 0. This, okay, 0.99, 0.01 plus 0.05, this times 0. I hope I didn't make any mistake in my calculation. Let me again do it. 0.99 times 0.01. Okay, all right, so it is 0.05. So you don't have to be worried. In fact, yeah, so this is how we apply Bayesian or Bayes theorem or Bayes law to solve real problem. In our next class, we are going to introduce ourselves to introduction to distributions. So we are going to start with discrete distribution. Thank you and enjoy learning.